Welcome students. So we are discussing problems related to work energy power chapter. The problems have been taken from Conscience Physics book ICC class 10. Now let us quickly move on to the first problem. It has been said that a stone of mass 500 gram is thrown vertically upward with a velocity of 50 meter per second. So first of all, let us write the given informations. So we are coming on to the solution number 1. Okay. So what are the given informations here? Let us see. So first of all, mass of the stone has been given, isn't it? Mass of the stone has been given. So what is the mass of the stone? Mass is 500 gram. If I just convert it into SI units, it will help to solve the problem easily. So it is 500 by 1000. That turns out to be half kg, isn't it? Half kg. Okay, and it has been said that the stone is thrown vertically upward with a velocity. So velocity of the stone, initial velocity u equals to, what is the velocity? Let us see, 15 meter per second. I think yes, it is 15 meter per second. You have to find out the potential at the greatest height, potential energy, kinetic energy on reaching the ground, and total energy at its halfway point. Okay, so given velocity, initial velocity equals to 15 meter per second. 15 meter per second. Fine. So first of all, we have to find out the energy at the greatest height. Now, this total problem is based on the conservation of mechanical energy. We know that for any system, the total mechanical energy remains always conserved. Mechanical energy has two types or two parts. One is the kinetic and is the potential. So there may be interconversion of potential and kinetic energy. Okay, there may be interconversion of potential to kinetic energy. But so kinetic energy may get converted into potential energy, and this potential energy may again get reconverted into kinetic energy. This may be the case, but the total mechanical energy remains conserved. But total mechanical energy, that is the summation of potential plus kinetic, Pe plus Ke, this summation for a system remains constant. Okay, so this remains constant. So this is the main fundamental concept to be used in this problem. Okay, so coming to the first part of the solution. First part of the solution will be something like this. You have to find out the potential energy at the greatest height. Okay, so when you are throwing the stone, what is the kinetic energy when you are throwing the stone? So kinetic energy when we are just throwing this stone, when throwing, so what is the value of the kinetic energy? It is equal to half mv square. So equals to half into m into v square. This turns out to be half into m is also half kg, and v square is 15 square, isn't it? Okay, so 15 square, it turns out to be, what is the value? 15 square is 225. So 225 by 4, this is the 225 by 4, this is the amount of energy when you are throwing the stone. 225 by 4 joule. Okay, so if you just divide this, it will come out to be something like 56 or 56 point something joule. Okay, so we're not going to decimal calculation. I think you will be able to solve the calculation part. So this amount of kinetic energy is being converted to potential energy when the stone reaches the greatest height. Hence we can say that the potential energy at greatest height will be equal to this kinetic energy, according to the law of the conservation of mechanical energy. Okay, so at the greatest height. Okay, so this is potential energy at the greatest height equals to, this is equals to kinetic energy, this is equals to the given solution 225 by 4 joule. Okay, so this is the first part of the problem. In fact, the second part of the problem says what is the kinetic energy on reaching the ground. So when you throw a stone, it goes up, it reaches a maximum height, stops there, and then again it comes back to the ground surface. Okay, so it has been asked, then what will be the energy, kinetic energy, when it again comes back to the ground surface? Definitely, as the energy remains conserved, so when it comes back to the ground surface, the kinetic energy will again be having the same value, so it will be also 25 by 4 joule, same amount of energy. And the last part is when the stone is halfway around, so it does not matter whether the stone is at a halfway point or at the greatest height, the kinetic energy and potential energy will get interconverted, but the total mechanical energy remains constant. So it has been asked that what is the total energy at its halfway point. So total energy always remains constant, so total energy at the beginning was 225 by 4 joule. So at any point midway, the also total energy will be same, that is 225 by 4 joule. So this is the answer. Okay, so I think the solution is clear. So the total solution is based on the concept of conservation of mechanical energy. Okay, now let us move on to solution number 2. So just we have to see what is the question asked in solution number in question 2, then we will be doing the solution. Okay, so it has been said that the diagram has been given. A diagram shows a sky jump. A skier weighing 60 kg stands at the point A at the top of the sky jump. He then suddenly moves from point A to B and takes off for his jump at point B. So we have to calculate the change in the gravitational potential energy of the skier between A and B. Fine. So we can say that, see here it has been given that okay, so you can see if you want to change the calculate the change in potential energy, so the height of the point A has been given, height of the point B has been given. So let us consider those are to be two heights. So let us write down the given informations first. So given is, first of all, weight of the skier is given. Okay, weight of the skier is given. So what is the weight of the skier? Weight of the skier is 60 kg. I think it's 60 kg. Yes, it is 60 kg. So let us say, and value of g has been given as 10 meter per second. So weight of the skier. So weight, we can say weight is equal to the mass into acceleration into gravity mg, and this part turns out to be 60 kg. In other words, you can say if I convert it in Newton, the value of g has been given as 10, so it will be 60 into 10, and that will be equals to 600 Newton. Okay, fine. Okay, then height at point A, height at point A. So let us consider it to be height h1. Let us consider it to be height h1. So height h1 turns out to be, what was the height? I think it was given as 75 meter. Yes, yes. So it's 75 meter. Okay. Then height at point B, it's given as h2. So h2 is equals to 15 meter. Okay, so what will be the change in potential energy between the point A and B? So first part of the solution, change in potential energy is given by the formula mg h1 minus mg h2. So you can take mg as common, h1 minus h2. So value of mg is 600. Okay, into height h1 is 75 minus 15. So it turns out to be 600 into 60, isn't it? This amount of joule. Okay, so this turns out to be 36, then 3 zeros joule. So this is the amount of energy, changing potential energy. Okay, now the second part of the question has been said that if 75% of the energy in part A, calculated in part A energy is 30,000 joule, so 75% of that, take it, becomes kinetic energy at B, calculate the speed at which the skier arrives at the point B. So let us consider the speed at point B to be V. Second part of the solution, let us consider, let speed of skier at point B be V. Okay, so you can write that half mv square, this energy has been formed from the potential energy, change in potential energy, and we have to take 40% of it. So 40% of what is the change in potential energy? 36,000 joule, isn't it? Okay. So from here you can say that half into 40%. Okay. If the mass has been given in kgf, okay, so you can weight has been given in kgf, so you can write from here that mass will be equals to 60 kg. Okay. Note that the mass given in kg is equal to the weight in kgf. So you can write the reverse also, weight given in kg equals to the weight in kg. So half into 60 into v square equals to 40 by 100 into 3 6,000. Okay, so here 20 cancels out, 20 cancels out, this 0 cancels out. Okay, and here cancels out 3, so you can write v square is equals to 4 into 360 by 4 into 360 by 3, isn't it? So from here you can write 360, so it's coming out to be 120. Okay, the value comes out to be 120, so you can say, okay, 4,100 into 36,000, that is equals to half mv square. So half into 60 into v square equals to 4,136,000. This turns out to be half 3, 0 cancels out. Okay, everything is okay, by 3. So this turns out to be 120 into 4, so 480. Okay, 480. So the value of the velocity will be something, v is equals to square root of 480. I think I will leave the calculations part to the students. So it will come out something to be, it's 22 square is 484, so it will be something less than 22 and greater than 21 square is 441. So this is the value of the velocity, this much meter per second. Okay, fine. So this is the solution. So I will just leave the calculation part to the students. Okay, we will solve it and you can also comment in the comment section. Okay, fine. Oh, sorry, I done a mistake. The energy conversion is 75%. Sorry. So here is one mistake. So it should be 75%. Okay, 75%. So if I just consider it to 75%, then the answer will be coming a little bit different. 75%. The energy conversion is 75%. So here it will be 75%. Okay, or this implies that half into 60 into b square equals to 75 by 100 into 36000. These 20 cancels out. Okay, or you can say v square is equals to 75 into 360 into 2 by 60, cancels out, this becomes 6, this becomes 6. Okay, so 2 into 75, 150 into, so 150 into, you have to find out 150 into 6, 650 the 90, so this turns out to 900. Okay, therefore you can say that velocity v is square root of 900, and that turns out to be 30 meter per second. So this is the answer. Okay, so I think all of you have rectified the mistake. Okay, so the answer is velocity 30 meter per second. Fine. Now let us come to the question number 3. So what is the question number 3? It says the hydroelectric power station takes its water from a lake whose water level is at a height of 50 meters above the turbine. Assuming that overall efficiency of the turbine is 40%, calculate the mass of the water which must flow through the turbine each second to produce and power output of 1 megawatt. Okay, so let us just first of all write the given informations. Okay, solution number 3. Fine. So what is the height of the river water? Height of the river water is given. Height of the river water, it is given that the height of the river water is 50 meter. Height river, no, it is lake water. Height is h equals to 50 meter. Okay, now we don't know the mass. Let mass of water be m kg. Okay, so the potential energy held up by this lake water is mgh. Okay, so you can say that the potential energy stored in lake water, stored in lake water equals to mgh. So its mass is m, h is 50 into h. Okay, now that means that the 40% of the energy is converted into output. So what is the output power given? First let us say what is the output power. Output power is 1 megawatt. If we just convert it into watt, this turns out to 10 to the power 6 watt. Now the time in which this output power is obtained is 1 second. So we'll calculate the output energy to be how much? 10 to the power 6 into 1 second. This turns out to be 10 to the power 6 joule. I think you have understood this formula. We know that power equals to energy by time, hence energy equals to power into time. So we have to so according to the problem we can say that therefore, sorry to get interrupted, therefore we can say that by the conditions given, okay, we can say that 40% of the potential energy, so 40% of m into g into h, sorry, h has been given as the height 50 meter, so this should be g. Okay, this should be g. Okay, into g is equals to 10 to the power 6, isn't it? So this turns out to be, or you can say that, or 40 by 100 into 50 into m into the value of this 10 equals to 10 to the power 6. 1 0 cancels out, this also cancels out, or you can say that mass m, let us write 10 to the power 6 as like this, 100, okay, let us take 1000 into 1000, you can write it 3 zeros each, by 50 into 4, so 50 into 4 turns out to be 200, so 1000 into 1000 by 200, this turns out to be 5, hence the answer turns out to be 5000 kg. Okay, so this is the solution. So how much is the mass of the water needed to generate an output power of 1 megawatt per second? It's 5000 kg of water needs to flow down. Okay, so this is our solution number 3, and with this we come to the end of this class. We have also completed the chapter work energy power. In the next class we will be discussing problems on machines. Till then, thank you.